Hello, and welcome to the first Maintenance and Reliability webinar. I'm Shannon Kiley with AIST, and this webinar is titled Making Sense of Maintenance 4.0. With all of the AIST functions, we must first go through both our antitrust and antitrust guidelines and anti-harassment policy. And before we do that, we'll go through these. Attendance audio has been disabled. Questions to the presenters should be submitted via the Q&A feature. These will stay during the recording and the presenters can view them after that. The host and moderator will determine which questions will be presented. This session is being recorded and will be available for broadcast afterwards. And if you have any technical difficulties, please contact training@aist.org. So the antitrust guidelines: do not discuss with others or your own or competitors' pricing. Oh, sorry. Do not make statements about your own prices or those of competitors. Do not talk about what individual companies plan to do in particular. Sorry. Oh, sorry. Okay. Do not disclose to others any competitively sensitive information. Do not propose or agree to any action intended to disadvantage or injure another company. Do not stay at a meeting or activity where any such anti-competitive talk is occurring. And the anti-harassment. I'll leave this up here for a few seconds. Okay. I want to introduce Carl Garringer from Steel Dynamics. He will be the moderator for today. Carl's a plant mechanical engineer at Steel Dynamics Structure and Rail Division. Having been with SDI the past 12 years, Carl's current role has him overseeing large capital projects, project engineering, technical, mechanical support for the mill departments, and driving safety improvements and initiatives. He is also the chair-elect for the current Maintenance and Reliability Technical Committee. Take it away, Carl.
All right. Well, thank you everyone for joining this webinar today. Today we're gonna have three topics to discuss. The first one will be what is maintenance and industry 4.0. Our second topic will be industry 4.0. Is this real life? And our third topic will be applied predictive maintenance 4.0. And now I'd like to introduce our three panelists. Our first one is Eric Almquist, who's a mechanical engineer for Star Tool and Die Works based in Chicago Heights, Illinois. He has more than 20 years of experience applying niche technologies into the metallurgical market for Star Tool and 3M Company beforehand. These days, Eric is leading new market development and technical sales for Star Tool's Young Industry 4.0 portfolio, focused on three technological fields: augmented reality, computer vision, and niche instruments for online process monitoring. Our second panelist is Greg Savernick, who is a product application manager at Quaker Houghton. Greg worked at U.S. Steel and Severstal NA as a reliability engineer for over the past 12 years. His broad range of experience covers asset management, tribology, project management, and process control across the metals, transportation, manufacturing, chemical, and refining sectors. He is a Six Sigma trained and is certified by the ICML. Additionally, he is certified in asset management, predictive maintenance, root cause failure analysis, delay performance improvement, and failure mode and effects analysis. Our third presenter is Jonathan Davis. Jonathan has led the Industrial Technology Research, also known as ITR, as CEO since 2008. In addition to managing the leadership team, he oversees ITR's core asset diagnostic and prognostic activities, key account relationships, and financial control. Over the past decade, the company has seen a high rate of revenue growth with annual earnings consistently exceeding industry benchmarks. For most of his career, Jonathan's particular interest and experience has focused on asset and system management through predictive analytics. Jonathan holds a BS in mechanical engineering and MS in manufacturing systems engineering from, I'm going to butcher this, is it Lehigh University? All right. And now Eric's gonna present on what is maintenance in Industry 4.0.
Thanks, Carl. Yeah, so I'm Eric Almquist. Thanks for attending today. A little bit about myself first. Like Carl said, I'm a mechanical engineer. I have lots of passion for this industry and for bringing new technologies to it. One of my favorite parts is identifying new technologies and making them accessible to the average person in the plant, and so that they understand, they can apply them and implement them. And implementing these new technologies is going to be increasingly important over the next decade, because reports say that by 2030, only 9.5 years from now, there's going to be severe skilled labor shortages across every industrialized country except for India. And so we need to implement these technologies. And Industry 4.0 is a buzzword that conveniently encapsulates some of these new technologies, but there's risk in that, is that if you're not communicating and you don't understand, it doesn't mean anything. And so I hope that my short presentation here will help that. And so share my screen here. Thank you. All right, share, sorry. There you go. I hope everyone can see my screen. What is part 1 of 3? What is Industry 4.0 and Maintenance 4.0? All right, I'm trying to advance there we go. So I think a lot of us view the Industrial Revolution as something we learned at school and is long ago finished and absorbed into modern life. And these are the images that evoke the Industrial Revolution for me. You have the belching smokestacks, the steam power trains, the child labor in factories, and the McCormick Reaper out in the wheat field. However, there's been an evolution in technology that all of us recognize. And about 10 years ago, a German government strategy think tank wanted to help their country, who is obviously a leader in industrialized modern technology, kind of brand itself. And so they developed what they call Industry 4.0. And so kind of reviewing this in that work that they did, they broke up, or they subdivided the Industrial Revolution into more of an industrial evolution, and with Industry 1.0 being that those images that we all think of as the Industrial Revolution with mechanized factories. But I think that most of us can agree that Industry 2.0 was kind of led on with the advent of greater, especially electricity and assembly lines, greater implementation of the technologies that are available to them. And then this German group delineated that the next kind of evolution or sub-revolution of the Industrial Revolution was after World War II, with robotics and automation. And now, here we are. We are in Industry 4.0, or at least what most of the industrialized world agrees with this German group from about 10 years ago. And the term Industry 4.0 was launched at the largest industrial annual fair called Hanover Messe in April 2011. And so what this is, the Industrial Revolution, Industry 4.0 is the 4th phase of the Industrial Revolution. It's not a thing, it's an era. It's an era of manufacturing with digital tools that interconnect the machines and workers. And to get a lot of the jargon out of the way and kind of take the power away from the jargon that sometimes frustrates me when people try to use jargon to kind of distinguish themselves versus communicate. It's the same thing as smart factory, manufacturing 4.0, interconnected enterprise, etc. It all means the same thing. And what it is this kind of I call them technology pillars around the branding of Industrial 4.0. And to make this more accessible, because that's what I like to do, think of you're building a house instead of having an industry. What do you need? What are the tools you need to build a house? So what we can do is we can say we need a hammer, we need some saws, we need a drill, we need some tape measures, etc. And replace in your mind those technology pillars with tools. And if you're building a house, you don't need every tool. You can subcontract some jobs. You can use a circular saw with a straight edge instead of a power miter box. So you can, to use the English phrase, you can skin a cat many ways, even though I like cats. So don't be intimidated by this kind of jargon. And some quick best practices about implementing Industry 4.0 is always start small and always start with what's called a digitalization team. That's basically a cross-functional team. And I don't want to get too far in the weeds here, but that's critically important so that your neat idea doesn't languish. You need a multifunctional team with a champion that sees the vision of building your industrial house, your industrial 4.0 house with the tools. And another very important thing is avoid the cool tech adoption temptation. We need to create success with tools, not just to say that we have them. And finally, very important is that these pillars, as I call them, these technology pillars, are not distinct. They don't live with themselves. They are a mesh of tools, it's almost more like a Venn diagram than a map of pillars. And the capability, your total capability, is going to be greater than the sum of each tool. So select the tools carefully with your digitalization team. Start small and expand. Now, maintenance 4.0 lives within Industry 4.0. And think of the best way to, in my opinion, to think about this is it's machine-assisted maintenance. And think about in the 60s and 70s and 80s when, for myself, I grew up working on my own car. I didn't have any diagnostic tools except for my ears and my eyes. And then came along OBD, onboard diagnostics, the little thing that you plug into your dashboard when you go to a car auto parts store to find out what's wrong and why your engine light came on. That's where we're at. Think of maintenance 4.0 as an OBD scanner for your steel plant or any industrial plant. Excuse me. And nowadays we have machines over here on the left that are talking to computers, and they're sending information to your HMI, your tablet, or your PC, and the operator has to interpret that data in maintenance 3.0. But maintenance 4.0 is now everything is meshed together, including the human. And in my case, Carl, thanks for mentioning augmented reality. Even though the worker is connected with augmented reality. So I hope that this quick overview gives you all listening and our speakers a basis to work from. So thank you very much. I'll stop sharing, sorry. And so I guess maybe I should pass this along to Greg.
Hello, all. Thank you, Eric. My name is Greg Savernick. In recent times, I was a senior reliability engineer in a fully integrated mill. My hot mill team and I applied Industrial Internet of Things, or IIoT, sometimes also known as IoT, to two different applications that I will cover in my presentation. So this is our story, as long as it goes. There you go. All right. So much like Eric had mentioned, there are things here that in this application of these two things, you can do both new builds and also legacy equipment. So it doesn't just have to be a brand spanking new item, and it doesn't have to be something that is older that kind of has been in operation for a long time but doesn't have a whole lot of telemetry to it. And so that is kind of the overall broad scope of what we were looking for. So the area of effectiveness basically was the Internet of Things. So it was using the ability to move data around. Cloud computing was another one of the functions that we use in system integration. And that's as shown on the graphic there on the pinwheel that Eric had proposed in the beginning there. And the whole thing is those three items aren't just the sole focus. So you have other things there. Say, for example, the augmented reality, that was another piece of that. so that you could actually get direct feedback while looking at a piece of equipment, as well as big data, because then as the information was being read through the telemetry and the condition of the equipment and all of that was then fed to a level 3 server for data storage and retrieval. So, you know, we had a historian, and that way that if we needed to do a review or look at something different, then that would give us the opportunity then to review it. On the first application, it was a brand spanking new item. So it's the most expensive to implement, but it also gives you the best blank slate to work from. So we took a system, so I should actually say it was literally 5 different systems that we took, and we had combined it and took 9 heavily energy dependent pumps, and they were like older style, and we replaced it with a modern single energy efficient unit using variable displacement pumps. The technology that was in place before, probably from somewhere around the 1930s. This here is definitely state of the art, and it really did help overall. We already had picked a standard platform. This is one of the things that when you're actually going through this, you want to make sure that you have a common platform for your IoT telemetry to talk to the people out in the field. So that was already in place. It was PTC ThingWorks is what we were using, and the channeling and visibility data was the key to getting useful information from those systems. So it was fairly easy to put it in there. There was a lot of heavy delay functions that were going on with this particular piece of equipment. So we wanted to make sure that it was fairly easy for anyone in the facility to actually have a look at this and see what's going on. So that way you had your operations, your maintenance, didn't matter who it was, you could all take a look at it and it was fine. So this way you could actually see and make sure everything was there. With this, we also made sure the telemetry was all the physical operating telemetry for flows, pressures, temperatures, levels, and any of the valve positions, things like that, feedback for the system that would allow us to see what the system was doing and in what function mode it was in when it was in operation. Along with that, we also put in online vibration and predictive analysis capability too. So this was a pretty large undertaking, and like I said, a pretty successful one, which I'll cover here in another slide. So the second application that we had was to retrofit a legacy piece. And this basically about maybe 1/10 to 1/8 of the price of new. But similar to doing this application, much like Eric had mentioned, you need a team. Kind of had the whole team get together. We figured out what our common goals were. And again, since we had that IoT platform already there, we took the principles of what exactly we were looking for to get information back from the system, and we developed a plan. And with that, we used one of our vendor partnerships with Flowcert, and you know, that worked out very well because they already had some of this type of technology in place, and you know, we were able to develop a plan then. So again, we did a series of sensors, the pressures, flows, temperatures, and this one we also did some power consumption, vibration, also that was sent into the IoT platform. Now, Flowcert used the same platform, and they also had a cloud-based monitoring capability, so you could actually see it you know, from your phone or anywhere else if you happen to need to do a remote check. But you also had the stuff that was in the plant itself. One of the things that was kind of a unique situation, since this was on the shores of the Detroit River, there is a high probability of fish incursion into that pump area. And the thing is that the fish, if they weren't properly caught, you know, ahead of time using a screen over there would actually start to infiltrate and cause a pretty significant delay. And it was fairly regular. About once a year, you would have this type of attack. Sometimes more severe, sometimes less severe. You know, again, typically in the fall was when this would happen, somewhere between the fall and winter, and it was a very common thing, and a lot of us wouldn't see it coming. So what we did with that was not only the sensors, but we also put a video recognition software that is very similar to what you see in today's facial recognition programs. And what we did was we used it for our machine vision system and monitoring the inbound debris. And it would actually trigger if it did see something coming across. And it would allow us to be prepared. And then along with the data, it was all synchronized together so that you could actually see not only the flows and all the other things, but you could see the sequence of events that something was starting to happen. And that would allow us to properly get that all set and get into and work on a plan to get everything brought back down so that we could clear out the fish and work on getting the system back online. With that, we also used a sequent automation process, which would integrate our IoT system with the mill radios, the cell phones that were used by the field personnel, desk phones, texts, and emails whenever a critical event would occur. And this was really quite helpful. So what we did was we had a process in progress. This is what this is. So we started to collect this data from both systems. And again, very similar type of responses. You had a little bit more vision on the new system as opposed to the old system, but it was a learning process. So we started to understand what the information meant. And as the information was flowing in, we would begin to see like nuances in the actual way that things would look from the information coming in from the machines. And these nuances helped us to see general trends for other things going on, minor things that we could address well ahead of any type of catastrophic event. So with that, this kept our overall impact low for our cost of operation. And as an example, the fish attacks were better managed at that point. So the whole thing is with this is how the data actually helped us move ahead. With the data flowing, we were able to use this data in reviewing process improvements, as well as actively act on information, to better our production effort. We'd use this data for morning meetings, business planning, maintenance, and other functions for Six Sigma projects to drive continuous improvement. So it gave us a lot of information that would help us to get through. So in the next to last part here, or actually this is the last part, the overall success. Our end goal was to improve the overall reliability for the production environment at our mill. Our delay rate for the one hydraulic system or the group of systems went from approximately around 3,500 minutes of delay for 1 year to under 90 total minutes after the unit was commissioned and put into full service. And with the pump house, we had a fish attack that started to occur we were able to properly shut everything down and mitigate the attack. Normally, we would have been down for a few days on a fairly severe attack, and sometimes as much as a week historically. In this case, we were back and running within a day, without any damage, without any issues with our furnaces, and it worked out really well. Now, the relevance for this too is the use of paperwork and generated reports that were usually required for printing went down, as you could see activity live on the screen. So you really didn't have to have it printed out unless you needed to do some, minor discussions. But in general, the live stuff was there, so you could just look at it. So again, it minimized the papers. Everything was recorded, and you could retrieve it, so you could actually do a historical report, and you didn't have to do any manual inputting. Also, the overall significance was with the ability to see what was going on live, our maintenance staff and operations staff was also able to anticipate these changes in the system and be able to be more effective and efficient in their work. This netted us a significant improvement in overall safety, operations, and maintenance effectiveness, and our cost per ton went down and our productivity went up. This basically was the full circle in reliability. And with that, I end my part of the presentation. I'll be handing it over here shortly to
Greg. Thank you for that.
And I'll be handing it off to Carl.
All right, thank you. And Eric, thank you for yours. I missed my cue earlier, working through some mute button technical difficulties, but now we're going to hear from Jonathan on his presentation.
Okay, thanks, Carl. Let me see. We'll get there. Okay, got it? All right, my name is Jonathan Davis. I'm with ITR. I'll pick up the story with Predictive Maintenance 4.0 and how artificial intelligence and machine learning are being applied in the condition monitoring and predictive analytics industry. So ITR is one of the original PDM companies in the world, and we first started providing vibration monitoring and analysis services to the steel industry in the 1970s. So we've seen the full evolution from the earliest days of predictive services to the state-of-the-art PDM 4.0 that's in use today. So for our industry, there's really two major opportunities, I'll say, is shifting the monitoring and analysis curve. So if you think of monitoring, that's where you trend certain features or parameters with the machine and check it against certain thresholds or alarm limits, and then you send notifications. That tells you when a process changed or the conditions of the asset have changed. But unless it's a very simple asset, it doesn't really tell you what to do or what the root cause was. You usually rely upon an expert to do some analysis, and from the analysis, you can figure out what actions are necessary. So if we can move some of those analytics further up process and even to the edge device, the equipment that's collecting the data, then it's a big win-win for everybody. The other is the inefficiencies of repetition of high-value knowledge-based work. And this is a challenge that every industry that is information-intensive has the same exact challenge. So that's where you have experts, smart people who are doing very value-adding work, but some of their work is maybe focused on more mundane tasks. If you can redirect them so that they're not doing those things, then again, it's better for everyone involved. So we'll talk about two case studies, offline route-based vibration analysis, monitoring and analysis, and an online system as well. So 3.0 to 4.0 in terms of PDM, what has changed? I think the two, Greg and Eric talked about some of these before. What I'll focus on is cloud computing and the accessibility of AI and machine learning algorithms. So for cloud computing, really we'll talk about the pooling of resources. What wasn't available, say, more than 10 years ago, or at least certainly not to the same degree, was the ability to go to cloud services and be able to pool all these computing resources and make use of data. So what's changed is we have a lot more data, and now we also have a lot more resources available. And as far as accessibility, what we point out here to a lot of people is that the underpinnings of AI and machine learning have really been around for 300 years. And if you think of modern statistics, it's really been in place for almost 100 years. But what's changed is that we knew what we could do with the data, but we didn't have the data and we didn't have the resources to really make use of it. And now those tools are available. So if we think about it graphically, in the 3.0 world, the expert would look at the asset and determine what data it was that they wanted to analyze or they needed to analyze. In the 4.0 world, and this was referenced in the other presentations, the data influences the expert. So a real quick word on types of machine learning. Sometimes they're summarized as 3 different types. I've seen as many as 10 or 12 different types. We'll keep it focused on 4. So unsupervised, supervised, semi-supervised, and reinforced or adaptive. So an unsupervised model, that's where the data is not labeled, an expert hasn't categorized it. And what we're trying to do is use the machine learning models to basically group or group the data together to find similarities. In a supervised model, you actually have labeled data, and that's where an expert has determined that this data means that or something similar to that. In a semi-supervised, and what I'll say about supervised is it's generally a better approach if you have it, but unfortunately, you don't always have labeled data or enough of it to be statistically significant. So you can sometimes make use of a semi-supervised model where you combine the supervised and the unsupervised. And lastly, we'll talk about reinforced or adaptive. This is where you're dealing with fairly complex systems that are hard to model, but you have almost like a reward system in the model so that it can constantly get better. So think of if you're trying to model an industrial system or self-driving cars or those kinds of things, that's where those tools really are beneficial. So for today's case studies, we're actually focused on the first 3 bullets. So our process objectives for any of our AI or machine learning projects are pretty straightforward. The one I'll focus on here is really the last one. I think the first bullets are pretty self-evident. So these are very powerful tools and you can do a lot of different things with it. But in our particular industry, where our customers rely upon us for telling them, not missing any problems with their machines and also not giving them any false alarms, 100% accuracy when using these models to try and improve a process is absolutely critical. And this it's actually a little harder than you might think, but it's certainly something that has been a core process objective for every project that we've worked on. So one thing I want to mention real quick is that when we talk about maintenance 4.0 or predictive maintenance 4.0 with customers, and a lot of people immediately go to online systems, smart online systems, and absolutely, that's a very critical part of it. But the offline work that we do, think of the portable data collectors where you go out, that is also a critical part of maintenance 4.0. And for our foreseeable future, I think it will always be part of what we do because there's just a cost limitation in terms of putting sensors everywhere in a mill and being able to collect the data you want. So there are a lot of smart sensors where the cost on these sensors have come way down, and there's certainly applications where that works effectively. In our industry, we rely very heavily on precision accelerometers, which are still a fairly costly item. So the hybrid approach of an offline and online system is something that we definitely want to do. So for 3.0 offline systems, it basically follows a PDCA cycle. The expert defines the data that they need, they collect it, they process it, they analyze it to determine, turn data into information, and then they go out and take whatever action they need to work on the machines. In a 4.0 offline system, the process is basically the same, but when you get to the analyze phase and then you determine information, we then digitize that information and relate it to the data that was underpinning the decision. And then, of course, we go out and take action. But then over time, we collect all that data. We also collect all the information and the correlation between those two. We build these machine learning models using that as our training sets. Once we prove that the models are effective, we then deploy them back through the process and even to the edge device. So a quick case study. This is something we've been working on for several years. This is from a flat mill and a beam mill where we have a little over 2 decades of history with them. It's a fairly large database of 800 machines. Back to one of the original objectives where we said we wanted to make better use of experts' time. Just for about 4 out of every 5 machines where you collect data, it turns out there's no issue with those machines, and you can't just disregard that because you don't know that until you've obviously until you've analyzed it. But if you could find a way to use machine learning models to pare that down so the experts are really focused on those 1 out of 5 or even 2 out of 5, then it's a big step forward. So the goal with this project, of course, was to discern between what was okay data or okay machines and machines that had issues, and we had to do it with 100% effectiveness. A little bit into the approach and the model. What we're going to highlight in the first image here is that on the left side of that is the information, is the expert's decision of, this is the data means this, and on the other red box, the red box on the right hand side is the data that it's correlated to. So over time, these are compiled and built into a database of expert findings. But as we talked about earlier, this is what we call a supervised model, or the basis of a supervised model. But sometimes you don't have enough. And even though we have 23 years, we didn't really begin our digitalization path until several years ago. And so in order to get enough data to make sure we were 100% effective and have a statistically significant result, we needed to also bring in similar data from other databases, other steel mills, and correlate it to this. Those two together, we get our semi-supervised model. In this case, we have a support vector model. We feed the data into that. We also then bring that into what's called a dynamic trust model. And the dynamic trust model is a way that we can tune the system. And for, I'm sure most of the people on the call today are, from working steel mills or very familiar with steel mills, and there's lots of transient events that occur in a steel mill. And you have to have some way to make sure your systems are sensitive to this. And the dynamic trust model, which we'll talk about in a little bit, helps us with that. So the output from this is that you either need further analysis or no analysis is needed. So they're pretty straightforward. If no analysis is needed, it's basically that the data has similar morphology and amplitude to other data that is okay. And the need for further analysis means that it's diverged. So what we see on the right-hand side is just one measure location, actually, that shows how the progression of the data. The green box indicates when it was okay. The yellow indicates that the model tagged it as something that was starting to show that there were issues. And the red is when the machine learning model flagged it and said, yep, we got an issue, and the expert also verified it. So a little bit of a summary of results for this project. Again, we've been doing this for several years. I just grabbed for the last 4 months for roughly around 22,000 measure events over that period. The model filtered out 90% without any measure of events related to potential failure machine faults being filtered out by mistake. So that's the 100% effectiveness for us. So, even if we were at 50%, it's a big step forward in productivity. And of course, as long as we have that 100% effective and we don't filter out anything that shouldn't be there. One thing I'll say about the offline project, just this project, the natural thing there is, okay, we've discerned between okay data and machines that have problems. we've also took this project a lot further, where the machines that have problems, what is the problem? How severe is the problem? We'll save that for another day, but we've had real good results with that as well. And in the interest of time, I just wanted to make everyone aware of that. Okay, so now to online systems. Again, everybody thinks of maintenance 4.0, they think of smart online systems, and that's a critical part of it. So just to compare and contrast 3.0 online systems, you know, and again, for a time frame, and I think Eric showed this, is that, you know, this is kind of like 2010 before is think of 3.0 systems. And to be honest with you, a lot of them, you know, are still 3.0 systems as far as I'm concerned. So we have a simple, you know, mill stand, motor gearbox, pinion stand. And then we have our monitoring system, which is collecting data from it. And the way our process works is we configure the system, then we put it in and we commission it. And in the commissioning process, we define the alarms for the data, the thresholds for the data. We then monitor the asset. We process the data, test the data, and then that sends the data somewhere and also sends out alerts. So typically tied into a PLC, there's usually an HMI or something similar to that. The HMI then notifies an expert. The expert goes and analyzes the data. And then based on that, they'll go to the machine and do some sort of corrective action. And they may even go back, the dashed line indicates they may go back to the system and, you know, update the alarms based on what they find. So in our 4.0 online systems, we really start the same way, and we'll highlight in red what's changed. So you notice that we only have 4 steps here, and we're a lot less concerned about the commissioning stage, because these systems are smart and they learn over time and they evolve over time. So we define the feature test, and if you think back to the, you know, the expert defining the data versus the data influencing the expert. In this case, the expert does begin the same way and says, this is what I think is important, but we'll rely more on the data also telling us what's important. So process is pretty much the same to this point. Then it goes to, you know, again, to the PLC and to an HMI, but at the same time, we also write that to a database. It's often in the cloud or in a place where we can take advantage of cloud computing services. So the expert's notified again, they go analyze the data, they do everything they were doing before. But as we talked about in the other step, the expert then, when they make a decision about what the data means, we digitalize that information and again, bring that into the database. So in the database, we have the underlying data, but we also have the information, and the information is the results of the analysis where they have correlated that this data means this, and it's been verified. When we have that, it becomes very powerful. At that point, then we're able to develop the machine learning models we were talking about. Those models can then move back to the machine that can actually implement it into the condition monitoring system. And if you notice, we changed the name of the system from a monitoring system or a CMS or a condition monitoring system to a condition monitoring and analysis system, because what we've done is we've actually pushed the analytics to the edge device. And again, this feedback loop is something that goes on and on for the life of the machine and the life of the asset, and the life of the system. So I'll walk through a quick case study here. This is for a PLTCM, particularly a 5-stand tandem mill. And we've had a system on here for a number of years. We actually do monitor the entire drivetrains. Just for the simplicity of the case study today, we're going to focus on it's also used as a chatter monitoring system. So most people on the call will be familiar with chatter in a steel mill. So third octave chatter is something that you know, it's very easy to detect. It's very easy to deal with. That's where the whole mill rumbles, and you know, you can speed up the line or slow down the line. But if you get into 5th octave chatter, this is a case where if you can actually imprint the steel, and it's not detectable except in a detailed quality inspection. And so this is a much harder thing to detect, and obviously something that's very important to customers, where the surface quality of the steel is very, very critical. Again, just to walk through the approach and model at a high level. So in this case, you know, what we're particularly interested in is picking out impulses and harmonics that are occurring in the signatures, particularly on the mill stands. What I'll say about this too is a lot of these systems that are in place that are more of a 3.0 system, they can be effective, but they're not 100% effective. So you can trend certain features like crest factor and try and look at peaks in the signatures, and they're useful. But over time, they're not going to be 100% effective. Whereas if you have an expert who can sit there and just stare at these signatures day in and day out, you can get to 100% effectiveness. And so the point of the machine learning model is that if we can capture that knowledge and actually put it and deploy it to the system that's on site, then we've in essence recreated having the expert and sit and just stare at the data. So our modeling, again, looking at the impulses, we're using a support vector machine, and on the harmonics, we're using adaptive threshold, feeds into our DTM, which I talked about before, very important. And are the impulses repeating or not in the time waveform? And are the harmonics in the spectrum or not? So we won't delve too deep into this, but just I know some people on the call probably, will find this interesting. As you can see in the time waveform, there's some very clear impacts that are occurring. What we use is the amplitude of the peaks, the envelope time waveform, and the dimensions of the mill. And we use a signal processing algorithm to locate the impulses. And once they're located, we feed them into the machine learning model and figure out if the impulses are repeated or not. For the harmonics detection, it's a little different process. We use the raw time waveform, calculate the Kepstrom. We again use the mill dimensions. And basically what we're trying to do is look at the harmonics that are occurring in the Kepstrom and relate them to the diameter and the speed of the work roll, intermediate roll, and the backup roll, and then say, is the peak location related to the bearing defect or the roll speed? If it is, then the harmonics are detected. If it's not, then there are no harmonics. So the dynamic truss model gets a little complicated, and there's a bit of machine learning behind that as well. But the concept is really that, and this is an important thing just to point out for people who are implementing systems, is you have to have something in the system that allows you to tune it or gives you some ability to do sensitivity analysis. And I think everybody knows this, cranes go overhead, there's just transient events that occur in a mill. And the way our model works is that based on different occurrences, the model starts at 100, and when some of these occurrences happen, then the truss drops, and eventually, based on the conditions, it'll drop past an alarm level, and that's when the notification from the system occurs. To just highlight it graphically for everyone, just we as human beings can look at the plot on the left, and you can start to see in the muddled time waveform the beginnings of certain impulses occurring. And the model picked it out as well and said, yeah, they're there, and it adjusts the truss score. And in the second one down, you can see that it's a little more distinct, and the third one down, much more distinct than the fourth one down. It's very distinct, it's repeating, it's absolutely there, it's been verified, and that's when the system sends a notification. And again, just to give you a quick summary on the results of this particular project. It's been in place for years. I just grabbed the last 16 months. We've had about 190,000 measure events, and just, there's a lot of talk about big data and all that. In each measure events, there are thousands of data points within those measure events, so we're dealing with very large amounts of data. During that time, we were able to detect 38 events that occurred. There were no missed problems. We did have 2 false alarms. Those were, in the end, not due to the model. We ended up having a damaged sensor, and once the sensor was replaced, the system was back working as it should be. So real quick, just summary, we absolutely are seeing improved condition monitoring through deployed analytics. We are able to move the analytics further towards the monitoring. We're able to deploy analytics at the edge devices. In the near future, we expect 100% accurate severity determination. In truth, we are seeing that in our projects now. We still have additional testing to have full confidence with that. Somewhat near future, the systems will also be able to spit out the recommended action. So not only do you have a problem, but what is the problem and what do you need to do about it? And what we always mention this because everyone always asks, okay, so you detect this bearing problem, what's the accurate projected remaining life? That is something that is lots of people are working on, including us. It's probably more distant than most people would like. But the way we explain it is there's no one today, no expert today who can tell you how long a bearing is going to last once you start to detect that you have bearing issues. And that's a little, if you can as a human being do it, it's hard to train a machine learning model to do it as well. So for our particular industry, as I mentioned, the cost of sensors, smart sensors have come way down. But in certain aspects, like when you're dealing with precision accelerometers, they have not come down as far as they need to. So we're pushing that, and hopefully we'll see those changes over the next few years. And the last is balancing data security and achievable results, because certainly any data that moves outside of a mill is, that's something that gives people a lot of angst. So, but there's also a lot of benefits to being able to take advantage of big data and the cloud computing resources. So, yeah, that's something that's striking the right balance to make sure that there's no risk to IP is something that we deal with all the time. So that's it. Hopefully, it was a little insight into how PDM or these tools are being applied to PDM currently. And if there are any questions, feel free to reach out to me.
Jonathan, thank you. Thank you very much for that. Throughout the course of the webinar, there's a few questions posed. We're gonna, with the remaining time that we have, we're gonna answer a few of those questions. This wasn't addressed to any one of the presenters, so any one of you guys can jump in here and run with the answer on this one. So, do you?
I can probably take this one.
Okay.
So, yes, there are always advantages to any type of data that you get in. It's just a matter of the output to see if there is actually any kind of relevancy there. And that's kind of the issue. If there is relevancy present, then yeah, it is kind of an important thing. More data is better than less data, but you also have to make sure that it's significant. And part of the protocol using an IoT platform that uses machine learning and things like that is to actually have and check to see if it's a significant piece of information. It can obviously tell you if you need calibration and stuff, but it is kind of, it can actually have some importance, but a lot of the general information has more broader reaching capabilities. This may be very specific to a task.
Greg, thank you.
I guess that one's for me.
That one is definitely you.
All right. So, yes, wireless sensors, depending on how you have it set up, some have remote capability, others do not. So they may be directly mounted. As long as you have an industrial grade wireless sensor, there really is no problem. As long as it's weatherized and capable of actually being attached and have positive tie-in to those systems, then yeah, it works fairly well.
All right, we have one more question that we don't have on a slide, but I'm going to pose it out to the three panelists. In all the mills that we go to, in all the conversations we have, we're well aware of the skilled trades gap. How does Industry 4.0 help decrease that gap, or does it increase that gap?
Can I try that one, Carl?
Yeah, absolutely.
Okay, so yeah, this is like what I think what both Jonathan and Greg said, that more data is better than less data. It's sorting it out. That's one thing of having data to teach. And skills gaps are about a lack of education and awareness and also just natural ability, but certainly education is the most important. And that comes down to the human, and without correct context around a task, the human can't learn. And so that's the real power of augmented reality, which is the HMI of our future. Augmented reality will replace your mobile phone in the next 10 years. It will replace many laptop screens and tablets, and you'll be wearing spectacles. Good or bad, it's something we have to navigate. But augmented reality is demonstrated many times, including Air Force studies and many other studies about giving information in context. As long as that information is authored correctly, in other words, that's the education data input, AR can definitely speed education and reduce errors. So I could keep going. I'm sorry, I'll get on my soapbox.
No, thank you very much, Harry. We had several other questions that were submitted. In a few days, when this webinar is posted, their contact information for our panelists will be on there, and feel free to reach out to them individually if your question wasn't answered during the course of the webinar today. So I'd like to thank everyone for attending. I'd like to thank everyone who took an hour out of their day to attend this, and a special thanks out to our panelists who truly made this possible. And Shannon.
Thank you, everyone.
On the screen here, we have some upcoming webinars that everyone should definitely get on the website and take a look at. And that's all I have.
Yep. Thank you, everyone.
Thank you, everyone.
Thanks, guys.
Thank you.
Yep.